Well, alrighty, we're on to transformations day 2. Yesterday we did transformations that shifted left and right or up and down. Now we're going to talk about different kinds of transformations. We're going to talk about multiplying by a number and what happens when we multiply by a number, our function by a number, because different things are going to happen. And there are some definitions that hopefully you picked up in class. If not, come see me and make sure that you get those written down, because you need the definition of stretch and compression. They're kind of important. So we're going to start, just like yesterday, we're going to use x squared as our original function, and we're going to compare everything to that. But the rules we're about to develop are true no matter what kind of function you're dealing with. We're just going to deal with the quadratic because it's the easiest to see what's going on. So we're going to start with x squared in our y1, and then the first transformation we're going to talk about is what happens if I do 5x squared. So I take the x squared and I just multiply the whole thing by 5. So when I graph them, here's going to be your parent function, and then here is the new function. And so you see it's inside of it, and so it's a skinnier graph. Now we have to talk about what that means in terms of a stretch or a compression. And so if you go and you look, second table or second graph, and you look at your y values. Your y values got bigger, okay? So they're moving up and away from the x-axis, because they're getting bigger. And so what's happening is that these y values are getting further and further away from the x-axis. So when you were looking at the picture, this got skinnier, but we call it a vertical stretch because the points are moving vertically away from the x-axis. And so we have a vertical stretch. So when I'm talking about what happens here, if a, the number that we're multiplying by, is greater than 1, so it's a number larger than 1, the graph narrows, because you can either say it got narrower, or you could say it vertically stretched. And what made it vertically stretch is what I said, is because the x values are getting bigger, so they're moving further away from the x-axis, and so they're moving further up, and so they're getting further away, so we are stretching the points away from the x-axis. So now we're going to do 0.3x squared. So we're going to go back to our calculator, same thing. I'm going to change this function, so now it is 0.3. Lost my point. 0.3x squared, and then we'll look at what happens there. And we're going to do the same thing that we did before. I think I forgot my squared. No, I didn't. There it is. You can see that now the graph is wider, and so my original one started and it got wider. And what you can see when you go over here to your table and you look at your y values, they're getting smaller, and so those y values are moving down and getting closer to the x-axis. And so I am compressing that graph vertically, and because I'm making those points get closer to the x-axis. And so when I describe this, if a is a number between 0 and 1, and I write this way, if a is between, that's an a, 0 and 1, the graph then widens, or it vertically compresses, because those points got closer to the x-axis. So now we're going to do the same thing, but now we're going to take it, we're going to make it negative, but unlike yesterday, we're going to put that negative inside the quantity, and we're going to square it along with the x. Yesterday, we just did a negative x, and we didn't make it a quantity. We didn't keep it all together inside parentheses. Something different will happen. If you remember yesterday, when I put the negative on it, it made my graph reflect across the x-axis. Today I'm going to put my negative inside the parentheses and then square the whole thing. And when that happens, here's what your picture is going to look like. And so they look like the exact same graph. Okay? It's really sort of hard to tell exactly what happened because they look like the exact same graph. And that is because if you go look at your table of values and you compare, your y values are exactly the same because I squared the negative. What we say happens in this case is that my graph reflected across the y-axis. But because my graph reflected across the y-axis and I'm dealing with a parabola, when it flips over the y-axis here, it's just the same exact thing. Unless I'd put a number in front or made it shift left or right, it would be hard to tell. But it's a parabola, it's going to look the same. If I were to do the square root function, you do not have to do this, but I'll show you. If I were to do the square root of x, and then I were to do the negative square root of x, so I were to do the square root of negative x, so I'm going to square root the whole thing. This one's easier to see. So there's your original, and then I reflected across the y-axis to make the new one. It's just harder to see that with a parabola, but that's what happens. So when I graph and the whole quantity gets taken to the negative, this then reflects it across the y-axis instead of, that's two S's, across the y-axis instead of across the x-axis. If the negative is outside, it flips below the x-axis. If the negative is inside, it flips across the y-axis, and so it flips left and right instead of up and down. So now we're going to put the number we're multiplying by inside the parentheses. So now instead of changing A, I'm changing B. If you'll look at the top of your notes that you had, when I do f times f of bx, that means I'm taking my function and multiplying the whole function by a number. Or I'm multiplying the x by a number, so I'm multiplying it by b. This multiplies everything by your number. This multiplies the whole the quantity gets multiplied. So now we have this. I've put it all in parentheses. I'm going to go back here and I'm going to change my function back to x squared because that's what we want to operate with. And then this time it gets to be the quantity of 5x. And then I'm going to square that whole thing. So my function becomes 5x. Instead of f of x, it's f of 5x. So when I graph it, just like before, when I did 5 times x, it got skinnier. My graph, my parabola is now narrower. But if you will go second graph and you'll look at your values, these did get further and further away from the x-axis. And so just like before, they were getting further away from the x-axis, but when you look at my graph, what I did is I took these points and I squished them closer and closer and closer to the y-axis. And so instead of stretching it up and making it reach, I squished it in, which is what made it narrower. And so this becomes a horizontal compression because it got skinnier, and the reason it got skinnier is because I squished it closer to the y-axis. I made those points get closer instead of stretching up further. And so here we are. What I'm going to say is if b is greater than 1, the graph is skinnier or we say that it horizontally, this time it's in and it's a horizontal instead of vertical, it horizontally compresses because now my y values are getting closer they're scooching in, and so they're getting closer and closer to the y-axis as I move in. That's what's happening to my graph. So then let's make b be a number between 0 and 1. We'll look at what happens here. So now I'm going to make my second one. It's still going to be the quantity, but this time it's the quantity of 0.3x. All of that is squared. And so when I graph that, you see that it makes my graph much, much fatter. And so what I did is I took all of these values that were on this graph and I pushed them way out from the y-axis, which is what made it wider. And so I took that one and I pushed it out, which makes a horizontal stretch because I stretched it out wide horizontally. And so when I say this one, if b is a number between 0 and 1, and that's how I write it mathematically, the graph is fatter or horizontally stretched. And here's how you are going to remember the difference between vertical stretch and horizontal stretch, or vertically compressed and horizontally compressed. If the number is outside of the parentheses, and so it's outside of the quantity, then it's vertical. If the number is inside the quantity, so it's in the parentheses with the value, or under the radical symbol with the value, then it is horizontal. Okay, that's how you will remember that. So let's practice a few. Just like yesterday, we're going to determine the function, plot it in one color, decide what the transformation is, and make a new color. These are out of order in your book. We're going to start with number 4, 5, and 6, and then come back to 1, 2, and 3. I'm not sure why the numbers are that way, but that's what we're going to do. So we're going to start with y equals 4x. Well, obviously that parent function is y equals x, which we will graph. And then when I do y equals 4x, since it's an a value, not a b value, because there's no parentheses, I'm going to vertically stretch it, which means I'm going to take all of these points and multiply them by 4. And so I'm still going to be at 0, 0 here, but this is at 1, 1, and I'm going to take that y value, multiply it by 4, so now it's at 1, 4. And this is at 2, 2, and I'm going to take that and multiply it by 4, so now it's at 2, 8. And I can go backwards and do the same thing. This one's not going to be at 4. It's going to be down here at 8. And so I have this new line. And so what happened is I have now vertically stretched that line because I have taken those points and stretched them away from the x-axis. I have moved them further from the x-axis than they were to begin with. Another way to say that is this graph got steeper. That's what we said when you were in Algebra 1, when you were dealing with linear. It just got steeper. But we're going to say, for the sake of using the same vocabulary, we're going to say that this has a vertical stretch, and the scale factor, which we're going to abbreviate as FSF, is 4, because that's the number we multiplied everything by. So we'll do the next one, y equals 2x squared. Well, obviously that is going to be a quadratic parent function, which is our pretty parabola. So we'll graph our parabola, and just like yesterday, you can go plot these in or graph them in your calculator and then go look at the table if you need point values. But if we'll remember that this is not a quantity, so this is just times 2, I'm going to take all of my point values and I'm going to multiply by 2. So this one will stay the same. 1 times 2 is going to become 2. And then this is at 4 times 2 is going to become 8. And so here's my new parabola. Vertex is in the same place. I didn't make a very good curve. But you'll notice what I did is I took these points and I have now moved them further from the x-axis. So again, I have a vertical stretch. So this is now a vertical stretch. And my scale factor this time is equal to 2. So we'll do one more. I'm going to pause and let you try this one, and then you can come back and check your answer just to make sure that you have it correct. So my parent function here is y equals x to the third, and so it's a cubic function. It makes this nice little thing, and then I'm going to cut everything by a third. So what I'm going to do is I'm going to squish everything by a third. That 0 is going to stay in the same place. And so here's my new function. And what you should notice is that I took each of my points and I moved them closer to the y-axis, or the x-axis now. I have squished them in closer, so this becomes a vertical compression. So I am vertically compressing because I'm moving it closer to the x-axis. So I'm vertically compressing, and my scale factor this time is 1/3. So we'll do a few more. So I have a cube root here. So we're going to do the same thing as the cube root of x, which is just what we just did, only on its side. It's the same function as before, but this one sits sideways because they're inverses of each other. And now I'm going to take it, I'm going to multiply everything by 2. So this one, and I've got to take everything and I'm going to make it bigger. So this one was -1, it's now -2. This one was 2, it's now 4. This one was 0, it's going to stay the same. This one becomes 2, and this one becomes 4. And so I'll graph my points. And so you can see I now took each point and I've moved it further away from the x value just like before. So this is another vertical stretch. And my scale factor is 2. So now I'm going to do this one, and I'm going to do the absolute value of x, and I'm going to do a -2. So this is going to be my absolute value function, which is really simple to graph. It makes this v. And now I'm going to do a -2 times that. Well, the negative, if you will remember, since it's not inside the absolute value symbol, is going to reflect it over the x-axis, and then everything's going to be multiplied by 2. Well, with the 0, when I flip it over the x-axis, stays in the same place, and when I multiply it times 2, it stays in the same place. This 1, however, I'm going to reflect it over the x-axis to here, and then -1 times 2 becomes -2, so it scoots down to here. This 2, I'm going to reflect over the x-axis and then multiply it times 2, so it's going to become -4. And so here's my new graph. And so it is reflected over the x-axis. And because I have now taken each of these points and I have moved them further away from the x-axis than they were before, it is a vertical stretch. And my scale factor is 2. It's not -2 because the only thing the negative did was reflect it, and we're not going to worry about that. So let's do one last one. This is going to be our square root function. And so here's our graph. This is what it looks like. And I'm going to take it, this negative will reflect it, and then I get to multiply all my values by 2. So reflected, the 0 stays the same, times 2, it stays here. Reflected, this point becomes here, that's -1 times 2 makes -2. I'm going to reflect this, so it's -2 times 2 is -4. And I'm going to reflect this, so that's -3 times 2 is -6. So here's my new graph. And so my transformations, again, it's reflected over the x-axis. And it's a vertical stretch, so I moved my points further away from the x-axis. Sorry for the bad handwriting. And the scale factor this time is still +2 because remember the negative just reflected. So let's do a few more word problems just to make sure we got this, and then I will let you have it and you can go on about your day. So the graph of the square root parent function is reflected across the x-axis and has a horizontal compression of 3. Horizontal compression, remember, means that I'm going to be dealing with a b value, so the whole quantity has to be multiplied by 3 and it's not outside the square root symbol, it's going to be under it. So we're going to start with the negative because it is reflected across the x-axis, and then it's going to have to be the square root, and because it has a horizontal compression of 3, that means I'm going to multiply it by 3, and the 3 goes under the square root to make it horizontal. If I'd put it outside the square root, it would make it vertical. So number 8, the graph of y equals the absolute value of the quantity x plus 8 plus 3 is reflected across the y-axis, and then it's translated 4 units down. To reflect across the y-axis, the negative has to go inside the symbol. So I'm going to start with my absolute value symbol, then I'm going to do -x plus 8. And then it says it's translated 4 units down. Well, that changes this k value. And so I'm going to take my 3 and subtract 4 because I've got to go 4 units down, which gives me -1, so it becomes -1. If I had wanted to move it to the left, then I would change this number, or to the right. But since it says down, I have to change this one. That's why I subtracted. Now the table one we went over in class. If you are still confused on how to solve this one, come see me in tutoring. Come talk to me before or after class or at lunch sometime, and we'll go over it one more time. But this one we definitely spent a lot of time on in class. So I will see you guys tomorrow.